Moving to the next part, after introduction, objective of this dissertation, I am implementing a prototype which is running on FreeRTOS environment. Real-time CAN driver is going to be implemented, as well as CAN to AWS gateway is implemented on the master node, interfacing of sensor to get the input status of the environment, and interfacing of the LED to get the status of the environment. Real-time data transmission from various node to the master node is the main objective of this dissertation. While doing the implementation of this prototype, I have gone through the various references paper. These are the few my base papers: monitoring CAN performance in distributed embedded system. In this, they are implementing a CAN application which monitors the CAN bus performance and error status on the CAN bus with the help of FreeRTOS. Another paper, design of parking guidance system based on embedded internet access technology. As we know that when wireless domain, we have protocol wired and wireless TCP/IP, UDP, DHCP. These protocols are used to transfer the data from one node to another node through wired or wireless communication. In the base paper 2, same technology they have used to transfer data from the application environment to the monitoring system. FreeRTOS.org is the source of providing RTOS utilities. LPCware.com is used to provide the various ARM related manuals and datasheets. Moving to the next slide. Features of the FreeRTOS. FreeRTOS is more to the hardware specific. It is scalable. It supports maximum up to 35 microcontroller architecture such as DSPIC 33, Cortex M3, M4, TDMI, ARM7. Its kernel binary image is just 4 KB to 9 KB, and it has operating system support Windows as well as Linux. Scheduling priorities policies provided by the FreeRTOS are preemptive, cooperative, and dynamic scheduling. The development tool which is used to get access of utilities of FreeRTOS such as Keel, LPC Express SO. These development tools are used to reduce the effort of porting of RTOS on the specific controller. So this development tool taking care of those porting part. Apart from if in the development we are getting any problem, we have a nice platform forum support from the developer side. They are always ready to provide the solution for the difficulties which is coming for developing any application on this RTOS. SourceForge and LPCware are the most dynamic forums provided by the FreeRTOS users and developers. Moving to the next slide. For this implementation of prototype, I am using the platform of FreeRTOS along with the LPC Express SO IDE. LPC Express SO is the integrated development tool developed by LPCware and CodeRed Technologies combinedly, and the stamp LPC1769, which is from Cortex M3 family, is developed. Hardware is designed by the embedded artist. So along with the FreeRTOS utility plus I am porting the RTOS on this stamp with the help of LPC Express SO IDE. The IDE provide the solution that it will become very easy to port the particular FreeRTOS on this stamp, and user need not need to follow the long procedure to doing this porting. Implementation of the prototype is based on FreeRTOS plus IO framework. As I am developing a CAN protocol driver, it is more related to the hardware specific. The CAN driver I am implementing on this FreeRTOS plus IO framework. Here, a FreeRTOS plus IO framework provides the skeleton framework that it will be helpful to implement any protocol driver with the help of this framework. Here I am implementing a CAN driver in consisting of FreeRTOS can open, FreeRTOS can IOCTL, FreeRTOS can read, FreeRTOS can write APIs. These APIs communicates from application layer to the hardware abstraction layer with the help of SIMSYS library, FreeRTOS library, and peripheral specific library. FreeRTOS plus IO is again another framework which provides the communication link of these APIs to the hardware layer. FreeRTOS plus FreeRTOS can open is explained in the next slide. This is the flow of the FreeRTOS can open. Here in the main.c file I am calling the can write task. In the can write task, the functionality of this task is written in the can.c file. Here I am first opening the can2 device. FreeRTOS open is the API is used to open any peripheral available on the controller. Here I am using can2. LPC1769 Cortex M3 has a can1 and can2, so I am choosing can2 for my application prototype. So it is a passing as an argument the protocol or peripheral name. Then it is goes to the FreeRTOS plus IO framework file. In that FreeRTOS device interface.c consisting one function FreeRTOS populate function pointer. These pointers taking the name of the device protocol prototype and the base address of this particular peripheral is taken from the BSP, that is board support package files, related files, and with the help of this pointer we are storing the base address of can2 and we are performing open operation on that peripheral, can peripheral. In the same manner, with the help of this populate pointer we can able to perform read, write, IOCTL operation on the same peripheral can2. The linking of the file is nicely taken care by this framework. Moving to the next slide. FreeRTOS can IOCTL. FreeRTOS can IOCTL gives us a facility to work our can driver as per the user requirement. Here various parameters are designed in for the can protocol. Among that, use interrupt means while using a read or write operation, whether we have to get data through polling mode or interrupt mode. That is the parameter designed in this first parameter. Again, we want to send data through standard ID or extended ID. Standard ID stands for 11 bit and extended 29 bit. Frame type, we can able to choose a frame which is whether we want to send a data frame or a remote frame with this parameter. Again, can is having a different mode for sending a data from one node to another, that is self-test mode, transmit priority mode, listen only mode. Among that we can able to choose the required mode according to our requirement. Acceptance filter is again a important feature of the can which is acting at the receiver side, whether we want to access the data from all node or we want to access the data from one node or we don't want to access the data. That is these parameters are designed by this acceptance filter. Can is having a payload of 8 byte. This payload byte length is designed or decided by this parameter. The read and write operation is again has the same flow which we have seen for FreeRTOS can open. Again in can.c we have the FreeRTOS read and FreeRTOS write operation. FreeRTOS read will able to read the data from CAN bus. FreeRTOS write is used to write a data on CAN bus. Here in the FreeRTOS write, if you want to transfer any data to CAN, then the CAN base address is taken from the here. With the help of the base address we are transferring data from user level to the hardware layer. CAN1 and CAN2 which is inbuilt in the LPC1769 controller consisting TDA and TDB register for transferring a data to the CAN bus. So data from user level is stored in these registers. These registers are 32 bit, each TDA 32 bit and TDB 32 bit. So together 64 bit data we can transfer at a time from one CAN controller. Same flow is for the can read task at the master slide, means where we want to receive the data. There we have to invoke this FreeRTOS can read API, and where we want to write the data, FreeRTOS write will work over there. Moving to the next slide. In this way, the protocol CAN is implemented. CAN driver is implemented on the FreeRTOS plus IO framework. Similar way, AWS stack is also implemented. This particular prototype is used for various embedded applications, among them elevator control system, industrial control system, parking guidance system. These are the principal applications for this suitable for this prototype. Sorry. Elevator control system consisting of the various inputs and outputs such as switches, floor number buttons, fan, alarm, and LED indicator. Industrial control system also consisting temperature sensor, gas sensor, smoke detector sensor, and monitoring system. So the data from sensor is to be transmitted to the host system in defined manner without errors. So the real-time CAN driver is helpful to transfer data from industrial environment to the monitoring system. The same case in the parking guidance system. To give justification to this prototype, I am focusing on application parking guidance system. This is the principal block diagram for this prototype, which is useful for the parking guidance system application. As we know that parking is a increasing issue in the various metro cities. We know that in function hall, metro, municipal corporation offices, corporate offices, and colleges, there is a always issue of parking when if a car user who needs to park his car at specific slot in the parking lot, he finds difficulty to get the empty space in the parking, and by doing this activity he loses his fuel as well as time, and due to this traffic congestion is happening. So this prototype is a best solution for these problems. In this block diagram, the CAN node A and CAN node B is implemented at the in the parking slot. Suppose at various places we have parking floor 1, parking floor 2. See, this CAN node A will be taking care of parking floor 1, CAN node B will taking care of parking floor 2. At each parking slot, one sensor is situated, and this sensor is checking the status. There is a parking car is parked or not, car is parked or not. So here this sensor will update this information to this CAN node A. CAN node will transfer the data from its to the CAN bus, and then from CAN bus master node, which will accept the data from the slave node, and it will transfer the data to the host with the help of AWS stack. At the same time, this data is transferred to the display unit. Display unit is fixed at the entrance of the parking. So here on the display unit, user can able to know who is taking his car outside. He can able to know the space and place available in the floor 1 or floor 2, and he can easily park his car at the particular allocated space without any help, and he will save his time, and accordingly traffic congestion will be reduced. One more thing, at the host side, the person who is monitoring this system, he is also able to know the parking status, that how many cars are parked and how many spaces are remaining. Apart from that, this user can decide which parking place we have to allocate for a VIP person. If any VIP person is coming to the this particular office, then he will vacate that particular space to the VIP person, so that that particular space is booked for the VIP person. This prototype application is divided into modules. The results I am explaining in the next slides. Implementation results for this application. Moving to the first module, GPIO sensor task. As I am developing this application on the FreeRTOS, I am dividing this work into different tasks: GPIO task, CAN task, TCP/IP task. Here, first task, GPIO sensor task. In this task, taking care of interfacing of sensor and LED at the slave node side. Here I am interfacing TSOP1738 sensor to detect the car object. In the first figure, here car is not present, means the space is vacate, so that this LED is on, and this is showing the places availability of the place in the parking lot. In the second figure, object, that is car, if car is present in that place, then this LED will not glow, means that space is not vacant. This interfacing is done with the help of GPIO protocol, which is inbuilt in the LPC 1769 controller. As we know, LPC expresses so IDE as having a console window to show the current status of the pins and register values. Here I am using this console view to see the output. I am sending a data of GPIO register, which is read from the FIO fast input output pin register. The status of that bit, the bit is status of the particular pin is that is interfaced to the sensor. So sensor status I am reading through the GPIO port pin. This port pin status I am sending to the CAN task through the queue mechanism. Queue mechanism is the IPC mechanism provided by the FreeRTOS. I am sending that data on the queue and receiving at the CAN task. Here the pin number 24 of port 0, I am interfacing a sensor. If car is not present, it will show 1. If car is present, it will show 0. So 1000 I am sending. This one I am sending through the queue to the TDA register, and again I am receiving a 0 when the car is not present, and when the car is present I am receiving the same value when 1 when car is not present. Moving to the next slide. Master to slave communication. Left hand side stamp, it is LPC Expresso board interfaced with sensor and LED, is acting as a slave. Right side same board I am using to get a data from slave to the master, is interfaced with RJ45 Ethernet cable to the host. The data from slave to master is transferred to the CAN bus, yellow and black wire, CAN H and CAN L. In the console view, I am able to send the data from slave to the master. If car is not present, means it will show that particular bit is high. If car is present, it will send 0. This data acquired at master I want to transfer on the host system. This is taken care by the TCP/IP thread. In the thread, I am creating a AWIP stack on FreeRTOS environment. So AWIP task is taking care of the implementation, sending a data from master node to the host system. In the first, when object is not detected, then this 24th bit is high. If object is detected, 24th bit is 0. Means object here is a car. If car is not present, that LED will glow, and on the host side at web server, I will get that the place is vacated. If car is parked, then it will show 0, and at the host side we can see that the space is not available. The communication from master to the host is happened through the IP address 192.168.10.2. So same information will be displayed on the display unit, which is fixed at the entrance of the parking, and designed application can easily able to show the status of parking to the person who is standing out with his car to park the car in the parking lot. Moving to the next slide. This is all system setup. Left side is a slave node, right side is a master node. RJ45 Ethernet cable is used to transfer data to the host. In my dissertation, I have published 2 papers: real-time embedded based drinking water machine and prototype implementation of real-time CAN driver for distributed embedded application in reputed journals, securing impact factor of 5.03. Here I am doing with conclusion that sensors and LED are interfaced with the GPIO protocol. Real-time CAN driver is implemented on the FreeRTOS plus IO framework, and data transmission from slave node to master node is possible without any error and according to the user requirement. The AWIP stack is implemented, and the data from master node to the host system is transferred to that stack. For implementation of this prototype, I have used this standard references from the IEEE monitoring CAN performance in distributed embedded system, AWIP stack protocol for embedded sensor network, parking guidance system based on wireless sensor network, parking guidance system based on embedded internet access technology, intelligent parking system for car parking guidance and damage notifications. Apart from that, I have gone through the various web references, freeautos.org, lpcware.org. To know the understanding of a CAN protocol, I am using a reference manuals of Robert Bosch, CAN specification 2, and CAN in automation, CAN specification 2. To know the understanding of AWS stack implementation, I have referred the thesis of Adam Dunkel's design and implementation of AWS TCP/IP stack. Thank you.